Good evening, everyone. I hope you had some knowledge from the previous lecture. So now we have with us Ms. Jyoti Verma. So it is my pleasure to introduce Ms. Jyoti Verma, an accomplished researcher and industry professional with over a decade of experience in bioenergy, CO2 valorization, clean energy technologies, and advanced hydrogen programs at the ONGC Energy Center. Ms. Jyoti is an engineering graduate and a highly recognized contributor in the clean energy domain. She has received several prestigious recognitions, including commendation from the Director General ONGC Energy Center and MNRE for her contributions to renewable energy initiatives. She has also been honored by ONGC for outstanding performance, consistently achieving a top tier PAR rating for 7 consecutive years. She has played a major role in national innovation and technology development activities, serving as secretary to the expert committee in MHRD AICTE Smart India Hackathon Energy and Renewable Energy section, and as an evaluator and jury member for major national innovation challenges supported by the Department of Science and Technology, with participation from over 100 engineering institutions across India. Ms. Jyoti has authored and co-authored more than 20 research papers and book chapters and has served as an invited independent reviewer for internationally published books by CRC Press, Elsevier, and Springer Nature. She is also co-editor of an upcoming Elsevier book on sustainable energy systems. Her research contributions span biofuel strategies, photocatalysis, plasma catalysis, hydrogen production, CO2 reduction, and environmental sustainability. She is also an inventor with a recent Indian patent application on carbon doped silica nanostructured copper oxide catalyst for plasma conversion of CO2 to carbon monoxide, demonstrating her active contribution to innovation in plasma assisted catalytic hydrogen production application in coal coal methane CBM wells, an area where she has made significant technical contributions and published impactful work. Her expertise bridges the interface of materials catalysis and energy systems, making her a highly valuable resource for this FDP. Please join me in warmly welcoming Ms. Jyoti Verma and try to interact with the guest and get some experience from her renowned many she is engaged with many renowned government organizations, so you may get some experience by interacting with her after her presentation. Ma'am, please you proceed with the presentation.
Very good evening to each and every one of you. And Dr. Bhargavi, thank you very much for a very nice welcome. I would first of all like to thank the organizers of the Faculty Development Program, which is sponsored by AICTE and ATAL Scheme of Government of India, being organized at NIT Raipur. I would like to thank Professor Naidu for efficiently coordinating this program. And my special thanks to Professor Suresh from NIT Bhopal, through whom I got this opportunity to present the work that I'm doing at my organization. So, the topic of my presentation is basically bioprocess for hydrogen production application in coal bed methane wells, which is primarily on the hydrogen energy pathways to a sustainable and decarbonized future. I'm assuming it has been a long and exhaustive day for each and every one of you. So I would like to keep my presentation very short and crisp so that you can grasp maximum out of it. And in case of any queries, please feel free to interrupt me in between. So I hope my slides are visible to you. So
Yes, madam.
Yeah, proceed,
yeah,
please.
yeah.
Proceed, madam.
So basically, I'm working at ONGC Energy Center, which is an R&D unit of the Oil and Natural Gas Corporation. It is based in Delhi. And since you all are aware that ONGC's primarily business venture is into the hydrocarbons. So the R&D center of ONGC is primarily focused on clean energy alternatives in the area of hydrogen, bioenergy, geothermal that I will shortly cover in the next upcoming slides. So the vision of ONGC Energy Center is primarily to harness science and technology to meet the national energy needs of tomorrow in a clean and sustainable manner. We have a mission that we would like to collaborate with the academic partners, the industry partners for jointly developing the technologies and processes that are used to the industries who are working in hydrocarbon sector for realizing the ambitious goals of the country towards its clean energy mission. So the motto of our company is basically from company to country to develop novel technologies that can be useful for the country to meet its carbon emission net zero goals. These are the broad areas that we are focusing right now. The organization was established in 2005, and since then, it's been 2 decades that we are involved in the areas of hydrogen, geothermal energy, solar thermal, produced water treatment, then biotechnology for energy and CO2 valorization, helium, uranium, and rare earth elements. We are closely collaborating with our academic partners, the industrial partners, and the prime focus is to bridge the gap between the lab scale technologies and the industrial scale technologies. Uh, so there are, as you are aware, that there are various TRL levels, technology readiness levels of the processes that we are working on to. Initially, we will work focusing on the projects of proof of concepts, which were mainly in that TRL levels of 1 to 3. So now gradually we are escalating towards higher TRLs from 4 to 8, and then from TRL 9, which is a commercialization aspect, and how we can identify the industrial issues rightly in the energy sector and in what way we can address it. We are trying to provide the infrastructure, the financial support, the bridge the gap studies for an effective technology that could be of use to the company and the country. So regarding, I think you must have heard that in the geothermal area, since it is not in the scope of the current talk, but still I would like to just share with the house so that because I am assuming that many students are also present during the seminar. So just to give you an insight that what all areas are there in the clean energy aspect. So recently you must have heard that ONGC has drilled a geothermal well in the Ladakh region, which is the first of its kind in the country to harness the clean source of energy because it is available 24 by 7 and it has a zero carbon footprint and towards the sustainable future, it is a really important aspect that our company has been doing. Then the next one is the helium, uranium, and rare earth. You obviously know how critical elements these are. Uranium, particularly, is an element that is used in nuclear reactors to produce power, clean power primarily. And our projects in this area are primarily focused on extraction of uranium, identifying the areas where high uranium concentrations are present in the country, high signature, good signatures where we are finding uranium. We are also finding the signatures of helium because they are radioactive elements and they are closely associated with each other. So, analyzing the areas, doing the drilling campaigns, trying to get them extracted through sustainable leaching methods. And also, of course, the rare earth elements, you of course know the ministry is right now focusing on the expansion of the rare earth elements extraction in the country. So we are trying to get these elements extracted so that clean source of energy can be harnessed within the country, supporting the indigenous technologies. The next one is produce water treatment. As you are aware, in hydrocarbon sector, whenever we are trying to harness the energy from subsurface conditions, which is coal or crude oil or natural gas, so there is always a lot of water that is associated with these components whenever we are taking them from beneath the earth's surface. So the water comes out with it, and this water is not fit for any consumption. Hence, it needs to be treated. It's a real menace how to treat this produced water, because it is carrying the hydrocarbon component in it. It cannot be purified just using the RO technology that we have in our homes. So special technology is required to get the produced water treatment done at a reasonable cost. So the R&D efforts are also focused in this area at our organization. Then hydrogen, of course, I'll cover in the upcoming slides, and biotechnology and CO2 vaporization also I'll cover later. Solar thermal area, we are working in the area of Stirling engine with the Baba Atomic Research Center, and it is a kind of sole top technology where beam down tower is being used, and research is also focused on this area. So coming down to the hydrogen program of our company. So with the launch of the National Hydrogen Mission, India is gearing up for meeting imminent energy transition with the help of renewables, where water and hydrogen are the key constituents. Now, OEC is set up by ONGC to focus on indigenous development of hybrid thermochemical water splitting processes for large-scale clean and green energy production. So, many others who are working on the electrolyzer system in the country for the production of green hydrogen, our approach is slightly different. We are working on the thermochemical cycles, so which are known to be less energy intensive and more cost economical in terms of scale up applications. So I will cover them briefly in the next slides. OEC has also been working in the area of hydrogen to develop cost effective technology that are ready to be scaled up to pilot scale facilities for the thermochemical cycles. The processes are different from electrolytic hydrogen generation, as it uses maximum thermal energy, about 80%, and minimum electrical energy in the process. If you must have heard that the definition of the green hydrogen, which is defined by the government, is for production of 1 kg of hydrogen. If the emission of CO2 is roughly 2 kg, then they classify it as green hydrogen. So you will find different definitions of green hydrogen in various parts of the world, but our country is following this standard at present. So we have been following a collaborative consortium approach involving various leading national centers of excellence like IITs, CSIR labs, technical universities to bring up these concepts to commercialization. NIT Bhopal was one of our collaborator in the past years. We have done many projects together. So OEC and its collaborators have also developed the supporting technologies for the processes with catalyst, membranes, electrodes, sensors, etc., that are useful in upcoming energy areas. So you can see the overall portfolio is like to develop a hydrogen ecosystem, not just the production of hydrogen, because many components are important in this. You have the material of construction, you have the infrastructure, what you are employing, what is the capital investment that is going into it, what is the operational cost that would be coming. So, cost economics is playing a big role in defining that what kind of technology, no matter how innovative it is, will be going forward for the commercialization aspect. Because, everything comes down to cost eventually, if you see from the industry perspective. Because if it is not profitable, for the investors, so the investors don't feel like putting in their funds for the scale up and commercialization. Then OEC has also won several national and international patents for developed processes and products for hydrogen generation. So these are the three main approaches that we are following in the thermochemical cycles, all the reactions and chemistries there. I'm sure we have got the experts who are well aware about these reactions. So I'll not go in much detail. So first one is basically closed loop copper chlorine cycle, in which the input is basically water, and the end products are hydrogen and oxygen. The entire other components, which is copper and chlorine, are getting recycled within the system itself. We are trying to couple this system with a molten salt system, which retains a lot of heat that is necessary for the reactions to happen in this particular thermochemical reaction. The temperature is approximately, it takes around 650 degrees Celsius. On the left bottom, you can see the closed loop iodine sulfur cycle. So, in this also HI decomposition, H2SO4 decomposition, and Bunsen reactions, these are the main primary reactions that are happening. And the end products, the input is basically hydrogen, and the oxygen and hydrogen are the output products. So the temperature requirements for this particular cycle is roughly about 800 to 900 degrees Celsius, which is quite high. Then the third one on the bottom right, you can see the partially open loop iodine sulfur cycle. So in this, the main component is hydrogen sulfuric acid, which has great commercial applications, and hence in this particular aspect the process becomes economical, because you are producing a commodity which already has defined commercial importance in the market, and the byproducts are hydrogen and oxygen. So this is the lab facility that we have developed at our Goa premises. It was a pilot scale facility. It is functional at 100 liters per hour capacity. We have done some batch scale operations. Now the continuous operations are required to analyze the data on long-term basis before we go for further scale up. At our we are planning the scale up at our refineries, because refineries are the primary consumers of hydrogen, be it refinery, be it cement industries. So there, whatever hydrogen we would be producing, it would be used, and we can ensure a proper ecosystem for the long run. This is the inside view of the lab facility that I had just shown previously at Goa. It's a closed loop metallic facility for hydrogen generation. The material of construction we are still working on, because the copper chlorine is quite a corrosive salt. So we are trying a range of materials using which we can scale up this facility further. So the next scale that we are planning to go for is 500 tons per annum. Then I'll come straight away to my topic, which is a bioprocess for hydrogen production in coal bed methane wells. Now, what is a coal bed methane well? So, as you can see, the coal bed methane well is a hydrocarbon well which has coal beneath its surface, but over the period of time, due to thermogenic um, processes, the coal has got converted into natural gas, which is methane. You all know that Indian coal is primarily a low calorific value coal with a very high ash content as compared to the superior qualities, which is anthracite and bituminous. in other parts of the world. India has lignite and subbituminous coal majorly. The underground coal gasification, which is a chemical process application, is yet to see light of the day. Why I'm saying this? Because underground coal gasification is a chemical based process, and we have been doing many white papers. We have been approaching the government to have some trials for underground coal gasification, because our honorable prime minister has already declared that our country is progressing towards gas based economy, because gas is a cleaner fuel as compared to coal, which is not considered as sustainable, if you see. So, giving you the context of Indian scenario, out of 33 coal bed methane blocks that are awarded to different CBM operators in India, 18 blocks are either relinquished or under relinquishment due to poor CBM prospects. Because the CBM production in our country is quite young, and we are still not having very advanced technology on how to take the optimum production to meet our domestic needs. Hence, as one initiative, since we are not going ahead with the chemical based processes, so as an initiative towards it, a microbial process has been developed by us for the enhancement of methane in poor to marginal producing CBM wells. What is marginal producing? When the well has produced over a period of time, say roughly about 20 30 years, the production eventually declines because you are constantly taking the gas from the well and the pressure is declining over the period of time. And after roughly about 20 25 years, the production is very low, and hence harnessing energy from the well is not very economically viable. So we leave the well in a proper closed condition, so that uh, uh, substantial pressure gets built up subsequently over next 5 to 6 years probably, so that we can take the production. So, our process that we have invented, it comes into picture when this particular well has been abandoned or it is producing poorly. So, our process, what we claim is that it improves the productivity and lifespan of the CBM wells, increasing the domestic gas production. So microbial processes for conversion of coal substrate, which is primarily a carbon source, to methane in producing CBM wells to improve the calorific value and its commercial viability is developed. In this process, the intermediates are hydrogen and carbon dioxide that further react to form methane in situ conditions. I'll show you the breakup of the reactions that are happening beneath the subsurface conditions, where coal gets converted to methane through intermediates of hydrogen and carbon dioxide. We have also developed some microbial bioprocesses for the conversion of hydrocarbons and hydrogen, and it is known as the bacterial biosurfactant producers. So there are some microbial population that are known to degrade the heavy crude oil in the energy sector, and these microbial population after degrading the heavy crude, the basically the wax component of the heavy crude oil, it helps to improve the fluidity of the oil, so that the oil can flow easily through the wells and we can take the production. So now how this happens? This happens by when the microbes consume crude oil, it converts it into hydrogen and carbon dioxide, which further gets converted into methane. So in this way, it helps us to recover the unrecoverable oil through microbial intervention. You must be aware that the maximum productivity that we can take, or the maximum energy that we can harness from a hydrocarbon well, is roughly about 20 to 25%, and if you have very good and advanced technology, it will be about 30%. So we cannot take the rest of the 60% energy that is there within the subsurface conditions. So, and this scenario is there in the entire world. Maybe US or some other countries who are in much advanced stages of the production, they can also take maximum 35 to 40% of the recovery. So, rest of the oil is in place where the energy has been harnessed. The main focus is to develop a microbial consortium with the capability of utilizing unrecovered crude or for generation of methane through the acetoclastic biological route that I'll be discussing in the next slide. This is just I would like to give you an overview of the coal bed methane market, which is the global industry and analysis forecast from 2022 to 2029. As you can see, from 2021 to 29 forecasting, the compound annual growth rate is of 6.5%, which is a substantial increase. And this just shows that the consumption of natural gas would be significantly increasing in the next coming years. The key players in this area I have listed. These are some companies that are actively working globally as well as in the country. Then, why natural gas is needed? It is needed for power generation, for fertilizer industry, for production of chemicals. And you can see globally, North America, Europe, Asia Pacific, there are very good producers of CBM gas, which is nothing but your natural gas. This is the current status of CBM operations in India. So we have been granted some blocks in which your auction happens, that which company would be taking the block and which company would be taking up the entire value chain production, since right from drilling of the well, maintaining the well, taking the production, doing the maintenance services, and then closing the well in a sustainable way. And the production rate, as you can see, it's 1.9 million metric standard cubic meter per day. The investment till date has been significant, which is 2.1 billion US dollars. The cumulative production of 5.7 billion cubic meters has been achieved so far. And 16 blocks are already on offer in 7 states. Uh, I'm sure as you can see in the map of the India, it's the eastern part of the country which is having the coal bed methane reserves. And most of the operations by commercial exploiters are focused in this particular area. And you can see the first block is West Bengal, and 3 blocks are there. Then in Jharkhand, 4 blocks are there. In Chhattisgarh, block 1, and in Madhya Pradesh, 4 blocks are there. So 3 stages are there, which is exploration, development, and production. Operators you can see ONGC, SR, Reliance, Indian Oil. So these are the names of few operators who are actively working in this area. And I would share the challenges that we face
Madam, you are muted.
can you hear me now?
Yes, yes, madam.
Yeah. So, this is the current Indian scenario in which you can see from financial year 2011 to 12 onwards, the production has increased from 8 times in the last decade, and it's envisaged to increase many folds in the next coming years. So this is one of the challenges. I would like to share the industry issues that we are facing so that maybe you all can also come up with more ideas on how we can tackle this particular issue where hydrogen is involved. In the picture, you can see a pipeline which is highly corroded, and this is called as this is due to microbial corrosion basically. So what happens is in the hydrocarbon industry, pipelines are there for obviously for the transmission of the crude oil or the gas from the source to the consumer. So these pipelines, what happens now? They get corroded. Now, what is the reason for getting corroded? Often we are encountering a microbial population which is sulfate reducing bacteria in the hydrocarbon sector, which is naturally present in the reservoirs. So, what this bacteria does, it's a very notorious microorganism, which tries to obtain energy by oxidizing organic compounds or molecular hydrogen while reducing sulfate to hydrogen sulfide. So, in a sense, these organisms, instead of oxygen, they breathe sulfate. So it leads to anaerobic respiration. So as you all are aware that hydrogen sulfide is quite corrosive in nature, so it tries to corrode the pipelines, and it's a huge it renders huge cost implications to the industries who are working in the sector. So operation and maintenance is becomes very costly affair, and changing the pipelines and getting them repaired is not an easy task because it requires a lot of financial investment. And these pipelines are passing through the rural areas where so many challenges are there. So the idea is to prevent this sort of microbial induced corrosion. So what we have done is we have developed a process where bacteriophages, which are primarily some sort of viruses that are being used to infect the hydrogen sulfate reducing bacteria. So eventually, over the period of time, the population of sulfate reducing bacteria declines. Since the population declines, uh, the hydrogen sulfide is not formed, and hence microbial induced corrosion is prohibited. Now, these microorganisms that I'm talking about, they are quite safe in nature, and we get their pathogenicity testing done before using them in any sort of applications in the industry, because you are aware that microorganisms over the period of time, through evolution, they evolved. They naturally develop ability to, you must have heard about the antibiotic resistance. Like we humans, if we take antibiotics very frequently, we develop the microbial antimicrobial resistance. So in a similar way, if we continue using the chemical inhibitors to reduce the population of the sulfate reducing bacteria, so over the period of time they become resistant as per the current industry practices. So this is one of the solution that we are working on, and field trials we are planning in the coming months in the unmanned platform. One of the major challenges getting the things done in the unmanned platform, because it is right in the mid of the sea where very less human intervention is there. So you cannot get manpower for each and every step, for each and every repair or maintenance mechanism, so their things are more or less automated. So these kind of technologies are very suitable for such industry applications. The advantages of using the sulfate reducing bacteria like bacteriophages over traditional chemical methods are they are specific to their host, and that means there are other populations also, but they will not affect the other microbial populations. In a way, they render a sustainable solution for mitigation of MIC. They are not affecting the indigenous microbial population of reservoir, which is very important because we don't want to interfere with the natural arena of or the natural ecosystem of the reservoir, because we don't we want the process to be environment friendly. So these phages can multiply exponentially while killing the SRB. They are environment friendly and they don't affect the quality of crude oil. This is very important to ensure before using any innovative solution in the hydrocarbon industry, because it causes huge financial losses to the company. Then reduced chemical treatments, and of course the operation cost is also very low. So, a brief overview I would like to give you about the coal bed methane gas. So, there are two ways of formation of natural gas during the evolution. One is, of course, the thermogenic, where under high temperatures and high pressure conditions, the coal gets thermally activated and gets converted into other hydrocarbon compounds, which methane is one of them. The other process is biogenic route. Now, there are some microorganisms that are known and reported. You can see in the published literatures, which are actively consuming the natural coal or carbon substrate, whatever is present under subsurface condition, and getting it converted into methane during their metabolic activity. So you can say coal substrate is basically the food for these specified population of microbes. You can see the role of the infinitely small is infinitely large because they can multiply really fast, exponentially. These are some chemical pathways just to give you a gist how this process really works. So you can see the coal is getting degraded by the hydrolytic bacteria into small, simpler molecules, polyhydrocarbons, monoaromatic carboxylic acids, ketones, single ring aromatics, and so on. Now, a next population of fermentative bacteria comes into picture. So you can understand it in a view that in millions and millions of microbial population, each one has a different role to play. Not every organism is converting coal into methane. There are others that are acting as an inhibitor. Like in this particular case, you can see in the second step, there is a hydrogen producing acetogen, which is converting the volatile fatty acid into carbon dioxide and hydrogen. This particular microbial population is of interest to us. Why? Because it is giving us the intermediates that will ultimately react to form the methane, which is our end product. Then there are other biological pathways also, which is the acetic pathway, in which the CO2 gets CO2 reducing acetogens come into picture, and they are converting CO2 and hydrogen into methane via the formation of acetic acid intermediate. Then there are fermentative bacteria. There is acetoclastic methanogens. So the hydrogenotrophic methanogens are of great importance to us because they are helping to facilitate the production of hydrogen in the subsurface condition. So they are naturally producing hydrogen, and hydrogen is basically the limiting factor in this particular process. If you are producing too much of carbon dioxide and the hydrogen is not getting produced in the appropriate mole ratio, then the methane formation would be very, very limited. So you can see the three methanogenic pathways that are leading to biogenic CBM production. I have listed the equations. You can also find them in various publications. This is the overview I would like to give you regarding the actual well site. Uh, Behind the people who are standing, you can see there is a hydrocarbon well. So the elongated vertical structure that you are seeing is the Christmas tree, what we call, and you can see it is the well area is surrounded by a cage sort of thing just to protect it from any unwanted human intervention. It's a very because these wells are present in the rural areas where and uh, the human intervention is quite high over there. So we try to have a limited access so that not everybody goes to the site. Proper safety protocols have to be in place. There is a attire that you need to be in because of course you know hydrocarbons are flammable, and you have to be in your helmets, your gears, shoe gears, and everything. So this is a picture of the sample collection that we were doing for the process. This is the methodology that we have adopted for bioconversion of hydrocarbons to methane. In the first step, we are preparing the anaerobic media in the lab. We are taking the media in the bottles to the field site where we are doing the on-site inoculation from the formation water. So the produced water that I mentioned earlier, it is having microbial population. We want to identify what sort of populations are present, if any population is of our interest, which we can target and get them multiplied. Then at the third step, you can see that we are doing the incubation of anaerobic bottles at roughly 60 degrees Celsius, because the subsurface temperature is roughly around 70 to 75 degrees Celsius, because these are thermogenic microorganisms that function better at high temperature conditions. So therefore, we have to mimic those environmental conditions in the lab facility so that we can help them to proliferate in a better way. In the fourth step, you can see some growth is there. You can see the bottle which is blurry slightly, and you can compare it with the one which is on the right side, which is quite clear. So you can see some growth is there. When you'll see in the microscope, you can always identify them. Then we are doing the scale up studies, and of course, gas chromatography analysis is there to identify what sort of gases are being produced by these microorganisms, and what is the proportion of those gases. Then further we do the scale up studies by water displacement method, and then we do core flood studies, and finally the feed application. Core flood study is nothing but it is mimicking the actual environmental subsurface conditions in the lab. Then this the primary challenge that we are facing in these sort of wells is high CO2 range, which is roughly in the range of 6 to 15%. So till the CO2 is in the produced gas is in the range of less than 6%, it is economically viable and it is of interest to the commercial exploiters. Once it crosses 6%, the economic value of the product gets declined, and it is very hard to find the buyers for such kind of gas, and it leads to huge monetary losses to the company. So to address this issue of high CO2 within the well under subsurface condition is of prime importance to us. As I had already mentioned, hydrogen is the limiting factor. Now, collection of formation water, coal and gas samples from well heads of CBM block is the first step. Then on-site inoculation that I had already covered. Then we do physico-chemical characterization of formation water, coal and gas samples to understand the microbiology of the samples collected. Then the very important thing is we need to establish the baseline production data and well history we need to know. What is baseline production is when we are trying to go to implement the process in the field in the actual condition, we should have a comparative data prior to the execution of job, which will help us to compare that our process has performed better, or it has not performed at all, or it has degraded the production further. That I will show you in the form of data in my next slide. Um, Further enrichment steps are done to identify the potential microbial consortia that are involved in methanogenesis process. Methanogenesis is basically the microbes that are involved in generation of methane. So, various recipes, nutrient recipes we are creating, and we have to identify that which recipe is working more efficiently and how we can optimize the compatibility with the formation water, because it has its own set of parameters such as salinity, pH, temperature, then various other microorganisms, and many other factors are there. So, it will help us to do the proliferation studies of hydrogenotrophic bacteria that is of our interest to us, and since it produces hydrogen. Then we also do carbon isotopic studies, which is a chemical test to identify that what is the percentage of biogenic methane and what is the percentage of thermogenic methane in a gas sample, so that we can compare, okay, that before the field execution of the job, the biogenic methane percentage was less. After the execution of the job, the percentage has gone up. Hence, our process has performed well as per expectations. So we do the response surface modeling to study the optimization of these nutrient recipes in the lab. Then presence of fermentative, methanogenic and non-toxic enriched microbial consortia by a metagenomic analysis. It is an analysis that helps us to identify what is the populations that are present and which population is of our interest. We can get this done through this metagenomic analysis. Then mass energy balance is there by exergy analysis, of course. Then we close the well after doing the field execution of the job for roughly about 30 to 60 days, so that substantial pressure gets built up. And when we see the pressure has built up, so we take the production from it. So some wells we have tested in 2000.
ये देखिए उनके घर का शानदार अंदरूनी नजारा। उनके घर की सजावट बेहद खूबसूरती से की गई है। इसे देखकर आप अंदाजा लगा सकते हैं कि
Yeah, please carry on, carry on. Hello, you are muted, muted.
So we have tested some wells in 2017-18, and they are still on production. We have observed 2 to 4-fold increase in the gas production through our process. So this is the core flood study setup that you can see. It's in lab for mimicking the reservoir conditions in the lab. These studies are done under anaerobic conditions in the absence of oxygen and limited air, because oxygen is toxic to these microbial populations since they follow the fermentative route. This is the metagenomic and toxicity study overview. You can see on the right, there is a list of microbial populations. Pseudomonas is there, Acetobacterium is there, Methanobacter, and so many and so on. You can have the access to this list. Then of course, the toxicity analysis is of prime importance, so that we are not interfering with the naturally present microorganisms, which could lead to any kind of calamity in future. So that is of prime importance. So this is the data that I would like to share with you all. The field jobs that we have done in the energy wells. In 2016, you can see the well was closed basically. So we were not taking any production from it. And the gas injection we were doing to just keep the well in live status. Then after we did the biostimulation job, the well was closed for incubation, and then when we opened it over a period of time, then we could see the gas production. As you can see, the net incremental value, which is standard cubic meters per day. So it is getting enhanced substantially. So, which is a signature that our process has worked efficiently. So all this implementation of the process is done in coordination with the asset on periodic basis for the testing. And we get constant support from them for post-job sample analysis and collection and intermittent period of testing and so on. So this is a video that I would like to play. I think it's a video, but I think there might be a problem playing it, so I will just skip it. So this is the pictorial representation of how a CBM well looks like. On the right, on the left, you can see the Christmas tree that I was mentioning earlier. So this is the subsurface, beneath the surface representation of the well. You can see the middle one is the annulus, and the tubing that is surrounding the annulus is called as the casing. We get gas and water simultaneously. So the concentration of gas is higher from the annulus, and the water comes from the tubing. So the nutrients are injected into the wells. I will show you the actual picture of the equipment that we are using at the site. And after incubation, enhanced CBM gas production is there. You can see the coal matrix on the right, and how the microorganisms convert it into various products that are of our interest. This is the actual site condition. You can see two wells over there. These are the skids that you can see. It's a kind of platform near to the well, and a skid is fabricated and kept. Basically, it has the flow meters, the gas flow meters, the water flow meters, the eco meters for analyzing the pressure conditions, temperature conditions, and other parameters of the well. And it helps us to it helps us to monitor the gas production via online facility. We have the display system at our offices, and any time of the day we can see that okay, the pressure has risen to this particular value, and it is a good time to open the well now to take the production. So this is another slide showing the execution of in situ stimulation job at the well site. On the top left, you can see there's a red truck. Basically, it's a injector unit, what we call. We do all the mixing of the bulk chemicals in the formation water using this injection unit. It is called as a WSS unit. So whenever a workover job is there in the wells, by workover job, I mean the well is clogged due to some reason and it is not producing. So you need to clear the casing and tubing which is there in the well, because it frequently gets blocked by the coal particles which are there. So you need to get those cleaned up so that gas can rise in the tubing. So on the top right, you can see the injection of nutrient formulation in the well. These are big tankers of roughly about 50-meter cube volume, in which water is stored. The formation water is collected 1 week prior to the job execution. And using this water, we prepare the bulk chemicals which gets injected, as you can see in the bottom left picture, the injection of nutrient formulation in well. So towards the bottom right, you can see this is the sucker rod pump, which helps us to put the formulated nutrient uh, in the well, so that after a certain period of time, the gas production gets enhanced. This is the graphical representation of the data that I had presented earlier, where in 2017-18 onwards, you can see a peak. So that is the peak production that we got. The red one is showing the gas. The blue one shows, the dotted blue line shows the water production, which comes simultaneously with the gas. Then you have in the orange dotted lines is the SRP, which is the sucker rod pump, which helps us to take the gas production from the well. Then CHP is of course the casing
बड़ी
head
मस्त
pressure.
आहे ना ती? बडी मस्त आहे म्हणलं. मस्त आहे म्हणलं. काजू बदाम वगैरे घातलं. महाग असेल ना?
So am I audible? So the dotted blue line is showing the dotted blue line is showing the casing head pressure, which helps us to analyze that okay, the pressure has risen. Now it is good time to take the pressure. So the gas production has increased from 500 standard cubic meter per day pre-job to roughly about 3000 standard cubic meter per day post-job, which is showing the efficiency of the process. The advantages of the process is that it is environment friendly. It involves minimum capital investment to generate biogenic hydrogen and thereafter methane in coal seams, and improving the productivity and longevity of the CBM wells. And the operational costs are very lower, and the carbon footprints are very lower. So naturally, it helps us to transition towards a cleaner gas-based economy. So the technology that we have developed has also received the uh, award from Department of Biotechnology, Government of India. Then we have also received appreciations from MNRE, and these are the few joint patents that we have for this process. These are some of my relevant publications that you can go through it. This is just to show you the on the right is the field picture where we are executing the job. On the bottom left is the GCS, which is the gas collecting station. It is where gas from various wells, it comes to a point so that it can be dispensed further to the consumer or the buyer. So usually companies like GAIL, they buy the gas from our company. Thank you. That's all from my side. And I would be happy to answer any questions.
Thank you, madam. From the participants, any questions, please? Anybody have any questions? Yeah. I think there is no more questions. If something is there, we will come back to you, madam.
Sure.
Maybe some other time we will discuss.
Yeah.
So before ending the session, we extend our heartfelt gratitude to the Jyoti madam for delivering an insightful and highly informative expert talk on bioprocess for hydrogen production application in coal bed methane wells. Your presentation shed light on the innovative biotechnological approaches for hydrogen generation and subsurface microbial interaction and potential of CBM reservoirs as sustainable hydrogen production sites. The depth of your expertise, coupled with the clarity of your explanations, greatly enriched the knowledge of our participants and stimulated meaningful academic discussions. We sincerely appreciate the time and effort you devoted to sharing your expertise with us. Your valuable contributions have significantly enhanced the quality of our program and inspired further interest in this emerging and impactful research area. Thank you once again for your esteemed presence and contribution to our event, madam.
Yeah. Thank
Thank
you
you very
so
much.
much, Professor Naidu, for giving me this opportunity. Thank you so
Yeah,
much.
yeah, thank you, madam. Good night.
Oh, good night.
Yeah, we'll see you, madam. Thank you. Bye bye. Participants, you have any queries or anything related to the program? Otherwise, we'll close the session today.
Okay, sir, you can.
Yeah, Professor Suresh, sir, thank you very much, sir, to joining us today. I think you might be there or you left. Okay, participants, do you have
Sir,
anything?
give the questions now only, sir, now itself, so that we'll prepare. Only 2 days have